All right, so today we're going to talk about sparse matrix vector multiplication. So in the last lecture, we looked at different sparse matrix formats and looked at how expensive it was to store a matrix in a given format and what formats made sense for what kinds of matrices. In today's lecture, we'll look at the sort of performance of different ways of taking these matrix formats and using them inside of a sparse matrix vector multiply kernel. So in the lab yesterday, except for a few technical glitches, we were looking at how to implement sparse matrix vector multiplication for the CSR format and also the ELL format. And we'll look at why the way that the simplest approach for the CSR format that we tried yesterday really isn't that high performance. It's very straightforward to do, but not high performance, and we'll see why that is today. Okay. So the first thing to understand about sparse matrix vector multiplication, like some people that you've seen have had numbers like 300 gigaflops, maybe 100 gigaflops. Sparse matrix vector multiplication, we really have no hope of getting that kind of number. And the difference between those kinds of kernels and what we're going to talk about today is that we are completely limited by our memory bandwidth. So there's sort of two dimensions. You can either have your performance limited by the floating point throughput, so just how many flops you can compute, or the memory bandwidth, so how quickly you can get data in and out of the main memory. And in the case of any kind of matrix vector multiplication, so in this case dense matrix vector multiplication, you are completely memory bound. And the reason for that is that anytime you want to do a floating point operation, so for each entry in the matrix, we're going to read a value in the matrix, we're going to read a value in the vector, we're going to multiply them together and then add them to some running sum for that row. So you're only doing two floating point operations, and you have to read at least one value in the matrix and one value in the vector. So with some cleverness, you can avoid reading all these redundant reads from the vector, but at least you have to read this value in the matrix. And that alone is what's going to kill our performance. So the thing that sort of guides us to is that we don't need to worry about shaving off instructions. We need to be solely concerned with how efficiently we access memory. And as I said, like sparse matrix, just like dense matrix, you're only doing one multiply add, so two floating point operations per entry in the matrix, no matter what it looks like. So the only thing we should really be concerned with, or the primary thing we should be concerned with, is how efficiently we're going to read the memory for the matrix and also the vector here. Okay. So as I said, matrix vector multiplication is memory bound. So a number that we would be happy with would be something like 20 gigaflops in many circumstances, especially if it's an unstructured matrix. The actual peak, you can calculate it on with pencil and paper pretty easily, is just sort of the memory bandwidth, the peak memory bandwidth of the device divided by how many bytes you have to read per flop. So you can easily produce a number, and for dense matrix vector multiplication, it would be something like 30 or 40 gigaflops. So 20 for a sparse matrix is actually quite good. So the way to measure, like we said before, matrix vector multiplication is memory bound. Well, how do we know that? Or if we said, matrix multiplication is floating point, it's bound by the floating point throughput, how would we know that? And one way you can calculate this isn't sort of an exact science, but it's sort of a first approximation, is the arithmetic intensity. So if you just add up all the floating point operations you're doing and sort of divide by the number of bytes you have to read from memory, you can get a reasonable estimate of how intense, how much arithmetic you're doing for the number of memory transactions. So in the case of matrix vector multiplication, you get an arithmetic intensity of something like 2 to 8 or 2 to 16, and this is quite low. We'll see how low this is compared to other things on the next slide. Question?
You're just calculating that as that's a lower bound for the arithmetic intensity. That's assuming that you bring in a vector entry from X and the matrix.
That's right. So this would be a lower bound for the dense matrix case. So if you naively pulled every operand from memory, that would be approximately what it is. I'll give some better numbers in the next few slides. Okay, So to get these numbers, like one thing that would be of interest, like there's the arithmetic intensity of your kernel, which is one quantity, and then there's also sort of what the device, the balance of resources on the GPU in this case. So one way to get a number, and this is not an exact number, it's just sort of a first approximation, is to take the peak gigaflop. So on a Tesla C2050, you get about 1 teraflop in single precision, about half that in double precision. And the calculation is simply to divide that by the peak memory bandwidth, which is about 140 on the same device. So if you take those and you divide it once, for single and double, you'll find that you get about 7 flops per byte in single precision, about half that in double precision. And this tells you that if your kernel, like if you do the same calculation for your kernel, and you get a number that's substantially above this, you're going to be compute bound. Your performance will likely depend just on how many instructions you can shave off. If you can find a way of economizing on your flops, you might get better performance. If on the other hand your intensity is much below this number, which is our case, then the only thing that's going to get you better performance is economizing on your memory bandwidth. So if you're firmly in one regime or the other, you really don't want to be concerned with reducing the use of this thing that's not binding your performance. It only makes sense to reduce your use of the thing that you're limited by.
Nathan?
Yes?
Shouldn't the number of numbers that you can transfer be different for the single and double precision cases? I mean, shouldn't your bandwidth effectively be half as much?
Well, I just did. I am sort of ignoring the width of the thing. So these numbers are correct, but you're right in that in many computations, the bandwidth demands would be tied to the width of the floating point type. So this just makes it much easier to do a direct comparison. Okay, so we calculated these numbers, so about 7 for singles, 3.5 for doubles. And if we look at dense matrix vector multiplication, you can sort of get a range. Like on the extreme end, it's the most naive method where you have to read in both the matrix entry and the vector entry, and you get to do 2 flops. So that's how you get a 0.25 in single precision. If you sort of say, I'm going to be clever, I'm going to use shared memory for this vector, so I only have to read it once, let's just completely ignore it. That's how you get a number like 0.5. So this is sort of the upper and lower bound. If you had effective caching or effective use of the shared memory, you could be towards the upper end. If you're unlucky, you could be towards the lower end. And that's what it is for dense matrix vector multiplication. So you can already see that these numbers are like 1/10 of the threshold. So we're way, way into the memory bound region. And it only gets worse when we move to sparse matrix vector multiplication, because not only do we have to read in the values of the matrix, but we also have to read in like the row or column index or some sort of metadata associated with the value. So we get even more abysmal numbers here. So the purpose of this is not, the exact figures don't matter. And you can say, well, on the previous slide we used peak numbers, and that's not really the achievable. It doesn't really matter. These numbers are so much different from the threshold between the two regimes that it sort of guides us to the notion that we should only be concerned with how efficiently we are using our memory bandwidth. So these are sort of the concerns that we should think about when developing sparse matrix vector multiplication kernels. We want to use our memory bandwidth as efficiently as possible. Another concern that I haven't mentioned much about, but we'll talk about later, is we want to expose lots of independent threads of parallelism in order to make use of the GPU and get the benefit of latency hiding and stuff like that. You need like thousands or perhaps tens of thousands of independent threads to fill the machine. So we'll see an instance where that doesn't immediately happen. We also would like to find opportunities for reuse. Anytime we can find a way of reusing a value, that's going to sort of amplify our memory bandwidth. So to first order, the performance of these kernels is based on our memory bandwidth consumption. So caching or more compressed memory or sparse matrix formats are going to give us higher performance almost immediately. So just to, oh man, you can't see that at all. What this was supposed to illustrate, and I guess it's hidden, is that if you have a block included, it's actually divided into different warps. So the warp is sort of the physical width of the machine. In this case, it's sort of 32 threads. So you can create a block of 128 threads, but when it actually enters the device and executes, it does so in batches of 32. And the important, thank you. The important thing about that is that controls how the threads access memory. The threads in a warp, when they access memory, if they do so in a nice contiguous fashion, then we get very good memory efficiency. If they access memory in a divergent fashion, then the efficiency goes down. And since our goal is to use memory bandwidth as efficiently as possible, we want to make the most use of memory coalescing and get the best efficiency out of that. So this is a sort of illustration of a fully coalesced memory access pattern. We have our threads in our warp, so 0 through 31, and they're accessing memory in a completely contiguous and aligned fashion. So this is the thing that would naturally happen if you had a big vector and you just said, you know, thread 0 reads the first element, thread 1 reads the next element, and so on. So this is the ideal access pattern, and if you have a kernel which accesses memory in this way, you'll get very good memory efficiency. You don't have to worry about it much at all. You can actually get, say, 90% of the peak just by doing this kind of thing. Question?
So when you say coalesced memory access, this is to the GPU's global memory. Is that true for all of the different memory subsystems of the GPU?
When you have something like shared memory, the thing you would have to be cautious of are bank conflicts. I don't think there are too many other concerns. So there are patterns that have higher or lower performance, but it's not so much the addresses. They don't need to be in a contiguous range. They could actually be pretty much anything. So good question, though. Yes.
Is there an amount of bytes for each thread for the coalesced memory to actually work?
Okay, so the question is, do I have to read a certain number of bytes? And that's a great question because, yes, there are certain quantities that do coalesce and certain ones that don't. And it is sort of changed on different hardware. So on the oldest possible hardware, it was very restrictive. You could only read, I think, 4-byte types, 8-byte types, or 16-byte types, and they had to be aligned. Anything other than that would give you disastrous performance. Nowadays, it's a little more flexible. So if you read any primitive type, so a 8-bit type, 16-bit, 32, all the way up to, basically like a double float or 4 floats, I guess. Those will all coalesce. So there's some restrictions, and they're fully documented in the CUDA manuals. But you can't just put a structure in there. That's where you come into some trouble. So good question. Okay, so less than fully coalesced, like this is a different pattern we're illustrating here, is sort of partial coalescing. So here we have some threads that are accessing, a region of memory, but there's a gap between them. And the way to think of this is that when we physically, when the GPU physically goes out to the memory, the DRAM, it's going to grab a big chunk of memory. So if you do this, it's really going to physically grab those things in the middle. It just doesn't do anything with them. It sort of drops them on the floor. So it's wasted, wasted bandwidth. Even though you're only making use of the 4 values on the left and the 4 values on the right, the GPU is still going to have to transfer these values in the middle. So this is less efficient than the previous approach where we used all the values. But it's still not terrible. Like, we're still going to get the benefit. We're going to use 2/3 of these values that we're fetching from memory. So it's partial coalescing. Another way that you can get, a suboptimal memory access pattern is if our values are misaligned. So here we have something that's completely contiguous. We're reading a set of values that all live in the same place, but we've offset. So instead of reading the first element of our array, we offset, 3 elements in this case. So this is another thing that can give us less than optimal memory efficiency. And the worst possible case is if we have our threads and they're just reading completely independently in memory. So if the reads that they're doing are separated by a wide distance, then we're not going to get any benefit at all from coalescing. And as I said before, you're going to go out, the GPU is going to go out and read a big chunk of data. You're only going to use one part of that. So it's very, very wasteful. So a neat sort of small benchmark you can do to better understand these effects is the following. This is just the SAXPY operation. So all it does is it reads a vector, multiplies it by some scalar constant, and increments an output. And what we're going to do is, instead of just doing this, where thread 0 reads the first element, thread 1 reads the second element, we're going to put a stride between them. So we're going to spread those out a bit. And what we'll find is that as we increase the stride, our memory efficiency goes down very, very quickly. So at the left, a stride of 1 is the ideal, coalesced memory excess pattern. And on this Tesla C2050, that gives us a result of around 130 gigabytes a second. So if you recall, the peak was 144. So this is a pretty good result. As soon as we go to a stride of 2, we get basically half that. So this means when we're reading memory, we're still grabbing big chunks of memory. We're just using, the even values. When we go to a stride of 3, we're using every third value. So the performance you get here, for the most part, is just 1 over x, where x is the speed of the most efficient coalesced transfer. Once you get out here, it flattens out. It doesn't continue to decrease. But you basically get, like 1/10 or worse of the total peak performance. So this is why doing, and I'll have a better illustration of this later, but this is why the CSR implementation we had in the lab yesterday is not the best. It's going to read values that are perhaps, stride 5 or stride 10. And that's going to put us, in the lower part of this chart.
So when you said that your CSR implementation is reading at stride 5 or stride 10, it's reading x at stride 5 or stride 10?
Yes.
Right, because the matrix itself is just still in this nice coalesced
That's right.
pattern.
So the main consideration, that's true. So there are two separate things: how you read the matrix structure and then how you access the x vector. I'm sort of ignoring the x vector for now because you could get lucky and there might be some reuse. It just depends on what threads are doing at the same time. But what really kills you is the fact that you have to stream this matrix in. And if you do that inefficiently, then that is perhaps, it's definitely a bad thing to do, and it's perhaps worse than doing inappropriate things with the x vector. So you could still get lucky and get cache hits here, but if you're reading with stride 5, I don't know. You were right. I can show you a benchmark later. Okay. So we had in the previous micro benchmark, we were reading with different stride. Here we can do with different offsets. And this is not such a profound effect anymore, but on previous hardware, it was. So what I've shown here, so the gray triangles at the bottom are the oldest GPU among these three. And this is what I'm talking about when I said it had, severe restrictions on the memory coalescing. If you did anything but aligned access to memory, you got a huge penalty.
I just like how it's 100% at 16, and then it drops right back down to 10% on either side.
Yes. So we lose, over 90% of our bandwidth just by, being offset by 1. And any offset other than a multiple of 16 in this case was going to give us that result.
Sure.
The next generation of hardware, so this GTX 280, improved on that greatly. So instead of being at 8 or 9%, we're up around 58% or so. So it's something that you wanted to take into consideration if you wanted the best performance. But if you didn't really care so much, just make an arbitrary read of memory, and you were okay. On the most recent hardware, I think this is an effect of the cache more than anything. You can get over 90%. So being misaligned in memory is no longer such a big concern. But in the previous ones, if you're running on your laptop or something, that can kill your performance. Okay, so there are different types of reads and writes that we're going to do. Different types of memory transactions. One type is when we read in the matrix structure itself. So if we have a CSR matrix, we have to read the row offsets, the column indices, and the values. So we have to read from those 3 arrays, and we just read from those. We never write to them. The other type of reading is from the x vector. So we're going to use our column index to go look up an entry in the x vector and then bring that in. And that's sort of unpredictable. So there are some things you can do to control that, but for the most part, it's just something you're given, and you have to accept the sparsity pattern that's provided to you. And lastly, you of course have to write out the results to the output vector and why. That consumes relatively little bandwidth because if you think about it, if a row has 10 entries, then you're going to do 10 reads or perhaps more to load in the data from the matrix. You're going to do 10 accesses to the X vector, and then you just have to write out one result. So there's relatively little bandwidth used when writing the Y vector, so we'll pretty much ignore that in today's discussion. So they're sort of ranked in the level of concern. Most bandwidth is going to be consumed just reading in the matrix. Some bandwidth, a significant amount, will be consumed in reading Y, but the amount used, a significant amount will be used in reading X, but relatively little for Y. So let's look at our CSR format and see why the performance we get if we take a naive approach to this operation is pretty bad. So this was the kernel or something equivalent to it that we wrote yesterday in yesterday's lab. And all we did here, actually this is the C version, normal CPU code. What we have here, we just loop over the rows, and then for each row we compute the sparse matrix vector product of that row, and then store the result in Y. To implement this with CUDA, the most straightforward thing is just to parallelize over the outermost loop. So instead of doing for each row, we just have a CUDA thread, generate an index, and then that thread is responsible for computing that row. So it's very straightforward. It's a relatively simple modification to the C code. But the reason it's a poor choice is that if you think about it, row 0, all the entries for row 0 precede all the ones for row 1, and so on. So they're contiguous. But if you think about how threads that are executing at the same time access memory, they'll do it like this. So the first thing that every thread will do is read the first column index and the first value in its row, and that's sort of what I've illustrated here. On the next iteration of this inner loop, so this loop, the threads will all be shifted over by one, except for thread 2 because it's done with its row. So you can see that the threads, the spacing between them, or the stride, is influenced by how long the rows are. So if the rows are pretty long, or even more than 2 or 3 elements long, then we're going to get very poor utilization of our memory bandwidth. And we're going to, if you recall that 1 over x curve, we're going to drop down that very, very quickly. So this is why the CSR kernel, and I named it CSR scalar because it just uses sort of a scalar approach for each row, doesn't perform very well. And if you completed the assignment yesterday, what you have found is that the CSR kernel is maybe 1/3 or 1/4 the speed of the ELL kernel. And we'll see why the ELL kernel does so much better, even using a very naive strategy. Okay, so a way to improve on the CSR performance is to use multiple threads per row. So remember that the warp is a group of 32 threads. One thing we can do to improve on the CSR performance is just use a warp. So we're going to use 32 threads per row. And in this case, the first row only has 3 elements, so we're going to waste the threads in some sense. But what the nice part of this access pattern is that the threads here are accessing coalesce in a coalesced fashion, a partially coalesced fashion. So if our rows are large, it's actually the opposite of the previous approach. If our rows are large, we're actually going to be grabbing big chunks of memory. So this kind of kernel, the CSR vector kernel, it still has some problems, but it can give us much, much better performance. And in particular, if the rows are large, it can give us quite good performance. And this is simply a fact of the memory coalescing. We're getting better use of the memory coalescing hardware, making more use of the values that we're fetching from the DRAM. As I mentioned, it's partially coalesced because the rows aren't necessarily a multiple of the warp length, and it's unaligned in general. It's unlikely to be aligned. So on old hardware, not such a great strategy. On new hardware, this is actually pretty decent. Oh man, it shifted. One difference between the scalar approach, so the scalar approach was nice because all we had to do was accumulate this running sum in a register. Didn't have to think too much about what other threads were doing. Our thread was independent of the others. The difference with this CSR vector kernel is that we compute a bunch of results, but the final result is stored in the registers of different threads. So we have the sum of the row is spread out in all the registers among all the threads in a warp. So what we have to do is we have to do a small reduction over the warp. So we have 32 values. We need to quickly compute their sum. So we have to do a parallel reduction. And I sort of illustrated, one pattern of doing a parallel reduction among 8 threads here. So this is just one detail. I'm not going to go too much into it. If you care to know the details, you can just consult the code in our library. But this is one sort of complication that arises if you use multiple threads, and then you have to go find a single value that they've all computed in parallel. Okay. So if we look at the ELL format, so this is a example one where we have some padding in gray. The nice thing about the ELL kernel is we can use a very similar strategy. We can do one thread per row, and if we are a little mindful of the way that we lay out this 2D array, we immediately get coalescing and we don't have to think about it very much. So this is why ELL. Like, not only is ELL attractive because it can be a relatively compact format in some cases, but it makes it very, very easy to pick up memory in an aligned fashion or coalesced fashion. So here I said we want to use column major ordering. So rather than going in CSR, we'd sort of go left to right and then down. In column major, we go down the column and down the first column and then down the second column. So the way to think about this is that the values for each row are actually sort of interleaved together. And that's why when threads go and pick the first value in their row, they'll actually do it in a coalesced way. So it's sort of the transpose of the CSR format. And for that reason, everything will be perfectly coalesced. If we want to do a little better, we can actually pad this out. So if suppose we want it to be aligned to a multiple of 8. What we could do is just add 2 more rows to this. We will ignore their values. They're just arbitrary. But what's nice about this is that when thread 0 goes to read the next value in its row, it'll be at a multiple of 8, and we'll actually get, in the case of the most recent hardware, it's only like a 10% bump. But on older hardware, it's maybe a 30 or 40% bump. So if you want the absolute best efficiency, you can pad your data structure to make sure it's not only contiguous access, but also aligned. The diagonal kernel, the layout is slightly different in the case of the diagonal, and we only have the 1 array instead of 2, but it really has the same exact structure as the LPAC, and we can use our padding trick here as well. So there's sort of 2 benefits of the ELL and diagonal format. One is that they are more compact. The other is that we sort of have the ability to lay out the memory in the most perfect way possible. So there's padding in there, and that's sort of undesirable. But for everything else, it's sort of the ideal thing to do. And for, if we go back and look at our CSR kernel, this was the simplest thing we could do, and it gave us poor performance. If we do this exact same thing, but tweak the body a bit, we can get a very, very efficient ELL kernel. So it's not only very efficient, but it's also very, very simple to work with. So the last format was the coordinate format. And remember, this is the one where we had 3 separate arrays. It was all the row indices, all the column indices, and all the values. And the way that we have implemented this, so you could do it in different ways, but the way that we've implemented this is by having every thread actually access one of the values of the matrix. So it's different than the others where we had 1 thread per row. In this case, we're actually going to use 1 thread per non-zero element. And that's going to be a little bit more challenging to sum up the values. But you can see that the nice effect of this is even if the rows are completely irregular, so 3 entries in the first one, 4 in the second, the way that we access memory will still be perfectly aligned and coalesced. So the complication that introduces is that we'll have these values sitting in shared memory somewhere, and we have to sum them up. But we don't want to just sum up values from different rows. We want to sum up the values within the same row. So that gives us this sort of reduction pattern here where we want to sum things, so we're going to accumulate values and try to sum them up towards the end of the row. But we have to be mindful of which values correspond to which rows. So there's a term for this, like I don't know how familiar everyone is, but there's a term for doing prefix sums, and then there are segmented prefix sums where we sort of stop summing once we hit a different boundary. And that's basically the same technique here. So we're going to sum all the entries in the first row, but we want to do it in parallel, and we do it by doing a similar reduction pattern. We just have to keep track of which rows we're using when we add them together. So again, if you want to know the full details of this, it's just a few lines of code in our library. Okay. So if we recall, we can sort of categorize each of these different kernels we looked at in terms of whether they achieve full coalescing, which the diagonal, LPAC, and coordinate do when reading the matrix. Partial coalescing in the case of CSR vector. So this is sort of a middle ground. If the rows are long, then CSR vector does pretty well. If the rows are short, it's not going to be so effective. And the CSR scalar, so the simplest approach for CSR, gives us, generally the worst performance. Question?
So am I missing something? If you interleave CSR and you pad, you get the same efficiency as ELL, but you don't have that listed or named, right?
People do have names for things like that. It depends.
Yeah.
Like there's one called the jagged diagonal, or JAD, which is sort of that way, but in order to not have to encode how many non-zeros are in each row, they sort the rows by their length. So any possible combination you can imagine probably has a name, and they would fit a middle ground between these. So you get maybe a little more metadata than CSR, but it's probably beneficial due to the better access pattern. So.
Yesterday we saw that in the CSR, it was like better in your examples, but here you see that they are full coalescing in the other ways of multiplying the matrix and the vector.
Mm-hmm.
And so it is because of the count, the amount of multiplications you have to do because of the matrix you have.
So I didn't quite get your question.
You have to make more operations if you use an ELL with a matrix that is not ordered.
Okay. Well, if I understand your question, like the ELL only works for certain matrices. So some of the time, like we would almost always prefer to use it if it makes sense because it's both simple and performs very well. The CSR is something that is more general than that. So people really like CSR because it is efficient to store their matrix. But what we found is that it's more difficult to actually compute with it. So if that doesn't answer your question, maybe we can
Yes,
just...
but we saw that we have a better performance with the CSR, but you have less coalescing. So this is what I do not understand.
Okay. Well, the performance that you might have seen yesterday for CSR would be a small fraction of the ELL. I don't know if you saw that or not, but CSR you might have had 3 gigaflops, ELL maybe something like 10 or 12. So that's where the different access patterns come into play. They give you very different types of performance. Question?
Is the memory allocated by Kulamalo always aligned to a multiple of the maximum quality?
Yes, it's guaranteed to be so. And it's actually a multiple of, it's not just like 4 times 32, it's some larger, like 256 byte boundary or something. But it's guaranteed to be something like that. Yes. Oh, question?
The via kernel, you avoid, well, there are fictitious elements. You avoid it to including the operations, or you put
Okay.
as a zero value and operate with them.
Okay, so the question is, what do we do with the padding here? We can actually avoid reading the padding in this case because we know if we're in this, first column that we know ahead of time because we know that these values live outside the matrix. We don't need to read them. So it's a little different. Like the diagonal kernel, we have to store these just to conform to the format, but we don't actually have to read them. So that gives us a little bit more of a boost. But in the LPAC case, we actually generally have to read them. So LPAC, we have to read the padding most of the time, or at least some of it. In the diagonal case, we know what padding we don't have to read. So.
But you put some code like if and then closes to avoid it?
That's right. So if you look at our code, I can point it out to you on our website. it actually has this. So it says, if I'm outside the matrix, then don't even bother reading these values. And you can do subtle modifications to this kernel too also. Like if you guaranteed that the padding, like once you encountered a padded value like a -1 or something, you wouldn't have to continue reading there. But it's a smaller benefit than it is in the diagonal case. Okay, so we've spoken a lot about memory coalescing. Now let's look at how many threads we actually have to generate to get good performance. And this is kind of interesting, although not as important as before. So we had different classes. We had kernels where we used 1 thread per row, like the diagonal, LPAC, and CSR scalar. We had another where we used 1 warp per row. And lastly, we had the coordinate kernel where we used 1 thread per non-zero. So if you think about it, these sort of have increasing granularity as we go from top to bottom. There's 32 times as many threads working on a row from the CSR vector to the ones on the top. And the COO uses sort of the most possible threads you can imagine using because it's using 1 per non-zero entry. It's kind of hard to think of how you'd use more than that. So an interesting benchmark you can do is to say, let's have a matrix and let's change the size. So let's start with a 2,000 by 2,000 matrix, and we're going to just use a dense matrix. So we're going to store a dense matrix in various sparse formats. And let's change the shape. So we're going to go all the way from a 1 by 4 million matrix all the way to a 4 million by 1 matrix, and look at all the different matrices in between. So the way to think of this is that it's the same amount of work. So if we gave this to a serial processor, it would take about the same amount of time no matter what the shape was, because it's the same amount of flops, same amount of memory accesses, and so on. But what it does is it changes the amount of threads that we can throw at the problem based on our previous strategies. So this is the kind of curves you get. So on the bottom, I've plotted different numbers of rows. So as we go from 1 row to 4 million rows, the number of columns changes in the opposite fashion. And what you can see is that we're doing the same amount of work. So, if I put a scalar, a CPU on here, we'd probably have a pretty flat relationship. But when we look at the different formats, we see that they have these sort of, curves, bell curves. And the reason for that is that if we look at, say, the ELL, we're going to use 1 thread per row. And it takes a certain number of threads to fill the GPU, as I said, about 20,000. So somewhere like right here. And if we look at the ELL curve, it actually takes about that many threads before we're really getting good performance. So if you have a matrix that has, just a few rows, even if it's really good for ELL, in storage sense, if it doesn't have enough rows, we're not going to be able to use this, straightforward strategy and get good performance anymore. If you look at the CSR vector, it's sort of shifted over to the left. And the reason for that is that it's using, it's finer granularity. It's using 1 warp. So about 30 times as much 30 times as much threads per row as the ELL kernel, and we can see that its performance, gets to close to the peak around 500 or so. So in both of these cases, it took about 10,000 threads or so to fill the device, and after that point, we were getting pretty good performance. What is interesting here, and this is sort of a nice result, is that the coordinate kernel, because it's doing 1 thread per non-zero, its performance is more or less constant, even though we changed the dimensions of the matrix pretty dramatically. So the COO kernel, even if we have 1 row or 2 rows, is going to give us, it's not the best performance overall, but you can see that it's much, much better than these other approaches when we have these sort of weirdly shaped matrices. And this is another reason. So the reason we made the hybrid format use the ELL and COO as opposed to, say, ELL and CSR is that anything you store in the COO format is going to give you a predictable level of performance, even if it has very strange structure. So you can think of it as putting as much as possible in ELL, throwing absolutely anything into the COO, and whatever you put in the COO will give you low performance, but not below some threshold. If we instead put it in, CSR, we could be down here, and that would actually give us, terrible overall performance. So anyway, the way to think of COO is that the performance is sort of independent of the shape of the matrix or its sparsity pattern. Okay. So this just summarizes what I said. The one thread per row strategy works perfectly fine if you have tens of thousands of rows. One wart per row is good if you have a few hundred. And then the COO kernel, which does one thread per entry of the matrix, is a very robust thing. It's a bit slower than the others in many ways, but it's a more robust approach. Okay, so we now looked at how many threads it takes to get decent performance out of these kernels. The last thing we'll look at is what opportunities for reuse we have. So as we said at the beginning, our performance is dictated by how efficiently we use memory. One way of making more efficient use of memory is to try to reuse any values we pull out of it. So if you look at a sparse matrix vector multiplication and our use of the values in the x vector now, you'll notice that in this case, we're using some of these values multiple times. We're using the first value 3 times because it appears 3 times in the first column. Using this other value twice because it appears twice in that column. So if you use values, especially if rows with similar that are nearby in the matrix use columns that are nearby in the matrix, you can actually get some benefit by caching the values of x. But this doesn't always work. In some cases, it can be sort of a bad idea to waste too much effort trying to do it, because you could have a matrix like this where some values are only used once, some values are never used. So you don't necessarily want to pull in a bunch of values just opportunistically. You have to be careful. Caching, it's sort of I think of it as just sort of a fortuitous benefit, because there's not all that much you can do to deliberately improve it in the most general case. On the Fermi architecture, so the Tesla C2050 that I showed earlier, has an L1 cache. So for the most part, you can just write a normal kernel, and if the threads happen to access values in a short period of time, you will hit the cache and you will save that memory bandwidth. On the previous architecture, so the G80 and GT200, in order to get this kind of benefit, you'd have to use the texture cache. So it didn't have an L1 cache, had to use the texture cache, but still it's a pretty worthwhile thing to do. And we saw as much as a 30% benefit by using the texture cache. An alternative to that, which sometimes works, sometimes doesn't, is to sort of just use the shared memory as a cache. So you just pull in some values. You check when you get an index, or when you get a column index, you check whether that column index corresponds to a value you pulled in, and if so, you use the shared memory. Otherwise, you go out to the global memory. So it's sort of like a user-managed cache in shared memory, as opposed to the hardware-managed cache in the L1. And the effectiveness of all these techniques depends on the matrix structure. So if you know something about your matrix, you might get great performance out of the L1. Maybe you can use the shared memory because you know you're going to fetch these values several times. It all depends on what your matrix looks like. So the last thing I'll say is that there are other techniques that you can use to improve reuse or improve your efficiency. One is if you have a matrix which has a block structure, so if you have, in this case, 2 by 2 blocks all over your matrix, then you don't need to store the column indices or the row indices for all of those. You just need to store one, and you say the next 4 values correspond to this block. So this is a good way of reducing the memory cost of your matrix and also the memory bandwidth required to read it. Another case, and this doesn't happen so frequently, is to use multiple vectors. And the reason that this is good is that before our calculation said we had to read in the matrix, and we had to read in, of course, a matrix entry, and we had to read in a value from x, and we had to do some floating point operations. In this case, we can actually use this value to do several flops. And if we had, say, 10 vectors, we would actually be able to use this value 10 times. So it increases our arithmetic intensity by a decent margin. And if you combine these kinds of optimizations, you can get a multiplicative effect. So, okay, that concludes our discussion of reuse. Here are some references. The first couple of papers are some we've written. This third paper is one that some researchers at Georgia Tech wrote about block formats, so the matrices like this one. And they can get a pretty good benefit from that, maybe as much as 50%. So it's definitely worthwhile to try. So, thank you. Are there any more questions?
I would actually just say that there's a really nice opportunity. If anybody just read this presentation or was excited by this presentation, PETSI has a preliminary implementation of sparse matrix vector multiply using Nathan's library. And there's some additional metadata that PETSI takes advantage of in finite element codes, where frequently in a multiphysics code, like Mark was describing, your data sits in these blocks of rows that look basically identical. So PETSI tracks this extra information as an inode, where it says, these things look the same. And it's perfectly aligned and ready to go for some very fast tuning on a GPU architecture. You could dive into the PETSI source tomorrow and start hacking on this. So if anybody's interested in this, this is an easy paper. You could do it in 2 months of work, including your write-up. So I just thought I'd point that out.
Okay. Question in the back?
Have you made use of this to implement an HPL?
You'll have to tell me what HPL means.
Lyntax benchmark?
No, as far as I know, there aren't really any standardized sparse benchmarks. There's a handful of them, but
Lyntax is a fairly widely used benchmark in the HPC community, and it's essentially DGEM.
right. But I mean, do you know of an analog of that for sparse matrices?
Well, I know that some have used sparse matrix techniques in order to get better performance out of that.
Okay.
And that's why I asked the question.
I see. All right. Well, no, I'm not familiar with that. But I know there have been several initiatives to do this, but the difficulty is you have to say what kind of sparse matrix matters to you. So I'd like to better understand what you're saying. But as far as just sort of, special purpose benchmarks for a sparse matrix vector multiplication, it's kind of difficult to say because everyone values a different kind of matrix. And you can tune to that and beat, other techniques. So anyway.